welcome to the next session of Strength of Materials. In this session, we are taking up the expression for hoop stress, that is sigma C, and longitudinal stress sigma L for thin cylinder. Consider a thin cylinder subjected to an internal pressure as shown in figure below. You can see here, this is the thin cylinder which is subjected to some internal pressure P, as you can see here from both the sides. And when there is a pressure applied like this, you will see that the material may break. It has a tendency to break. So in that case, if it breaks, this is the surface which gets exposed. And you can see that this is the surface which was resisting by showing the generation of stress, which is called as sigma C, that is hoop stress or circumferential stress. Now why is it called so? Because when this pressure is applied, you can see a change in the diameter. When the diameter changes, also the circumference is affected. Hence, it is named as circumferential stress. Due to circumferential stress, the cylinder has a tendency to burst into two parts as shown in figure 3a. Now, we will talk about the bursting force which is caused by this pressure P. Now, we are well versed with two formulas. One is pressure is force applied upon area. When pressure is applied, the material will show generation of stress. So generation of stress or stress formula is resisting force. Now whatever force you apply is the same resisted value here upon cross section area. So when you talk about bursting force, we are going to talk in terms of pressure. And when we talk about the resisting force here, we are going to say it is sigma into A. So let me call this as Fr and this as F. So this is bursting force, say F. This will be pressure into cross-section area, as you can see from here. Now let the pressure be P itself. When I have to talk about the area on which this pressure is exerted, it is going to be this diameter D, as you can see, and it is over the entire length, that is the body is breaking. So this will be D into L, PdL. Now let's talk about the resisting force. Say I call it as Fr. This will be sigma C into area. Now here the stress is sigma C. So I call it as sigma C into area. So this will be sigma C into. The sigma C, you can see it is exerted over this entire length and on this thickness T from both the sides. So I can say it is 2T into L. Now for equilibrium, that is for the cylinder to not break, obviously these two forces should be equal to each other. So I will write for equilibrium, I'll have bursting force will be equal to the resisting force. So I'll have bursting force PdL is equal to resisting force sigma C into 2T into L. Now this L gets cancelled from both the sides. So what remains as the formula for sigma C is PD upon 2T. This is called as circumferential stress for the thin cylinder. Now let's talk about another figure 3b that you can see here. When the pressure is exerted on these cross-section areas that you see, like we discussed before, when the pressure is applied here, the cylinder will have a tendency to break from the center. So I am applying pressure P here sideways such that your cylinder is breaking and it is developing a longitudinal stress. So for this case, when I talk about the bursting force, which is again caused by P into the area. So this is my F, P into. Now this area, as you can see, is pi by 4 d square, that is a cross section area. Now when I talk about the resisting force, Fr, this will be sigma L into A. See to it that you change the sigma L and not write it as sigma C. So this becomes sigma L into. Now when you see this stress being generated, the area over here is pi d, that is the circumference, and this value of T, thickness. So I can say it is pi d, that is this circumference that you are seeing over here, the circumference and this thickness on which you are seeing the effect of stress. So for equilibrium again, I'll have F equal to Fr. That is, bursting force will be equal to my resisting force. Therefore, P into pi by 4 d square will be equal to sigma L into pi dt. This diameter gets cancelled. This pi value also gets cancelled. So what remains as sigma L is Pd upon 4 and this T. Now let's see the shear stress that is generated, or we would rather say that the maximum value of shear stress is what we want to calculate on the thin cylinder. In a thin cylindrical shell, at any point on its circumference, there are two mutually perpendicular stresses. Now if you observe carefully, you had two axes x and y. In the y axis, you saw the effect of sigma c, and in the x direction, you saw sigma l. So if you have two mutually perpendicular stresses, these two are called as principal stresses. Principal means something which is main. So here you will have a main stress in the y direction, that is the circumferential stress, and in the x direction the main stress is my longitudinal stress. We just found that this value is maximum and this value is minimum. When you talk about principal stresses, one has to be max, one has to be min. So when we are talking about the formula for maximum shear stress, by using this principal planes and principal stresses concept, tau max is going to be sigma max minus sigma min upon 2. Now here your sigma max is sigma c, sigma min is sigma l upon 2. So I'll just fill up the formula. Sigma c is Pd upon 2t, sigma l is Pd upon 4t upon 2. Let's take LCM over here. So this becomes 4t as the LCM for both of them. This will be multiplied with 2. So 2 Pd minus Pd, and this 2 also is there. So this becomes Pd upon 8t. So I can say that shear stress for thin cylinder is given as Pd upon 8t. This is another formula which you can note down, which will be required for solving of numerical. Next we'll talk about the change in dimensions. That is, there will be change in diameter, there will be change in length and volume. So there will be some change in volume that you will see of cylindrical shell due to the internal pressure. Hoop stress and longitudinal stress are two mutually perpendicular stresses. They produce strains longitudinal and lateral. Now this is something which we already know from the chapter of uniaxial, biaxial and triaxial loading that we have already studied. In that chapter also, we used to say that if we have a cylinder, say if the load is applied in this direction, so the length is going to change. So the length becomes the longitudinal value and diameter becomes the lateral value. That is, the main effect will be on length, and diameter is something which will see a consequence. Because of this change, obviously this diameter has to reduce. Only then you can say there is an increase in length, because I am not adding material from outside. We are just seeing a change in length, that is increase, because of diameter shrinking. Same way, suppose if the cylinder is now subjected to a load in this direction, you will say that the diameter is going to increase. Now the compensation for this will be length decreasing. So that is how the things work. So that is called as longitudinal, which is main, or the direction in which you apply the load. Along that direction, whichever dimension you see, for example L for the first case, here L becomes longitudinal and D becomes lateral. For the second case I have drawn, here length becomes lateral and diameter becomes longitudinal, because that is the direction in which you are applying your load. So we also have two cases. So let's say that mu is the Poisson's ratio that we are going to use. Now if you recollect, when we talk about circumferential strain, that is EC, this will be sigma C upon E. This is a basic formula. Now this is the direction, circumferential is the direction in which you can see the effect of your load. Now, which will be lateral in this case? It is mu into sigma L upon E, because this becomes the lateral direction, and we know that mu is the ratio of lateral strain to the longitudinal strain. So when we talk about lateral strain, here lateral will be sigma L and longitudinal will be my sigma C. So this is the formula which we are going to use. You can just refer back the chapter of uniaxial, biaxial and triaxial loading. You will get a clear picture of this formula that I am using. Now we also know that this formula of sigma C is PD upon 2T into E minus mu PD upon 4T into E. Suppose if I take PD upon 4TE as common from both of them, this will be 2 minus mu. This is the formula for EC. Now if you recollect about circumferential strain or stress, at least circumferential stress was because of your change in diameter. If you recollect, this is my cylinder, and suppose if there is stress in this direction because of the pressure P, my cylinder was breaking like this in between, and the circumference over here was getting affected. So when the diameter gets affected or inflated, my circumference was getting affected. So I can say that this EC will also be delta D upon D, that is change in dimension upon original dimension. And the dimension here we are talking about is the diameter. So therefore I can say delta D upon D is also equal to PD upon 4TE 2 minus mu. Let's say this is equation 2 and this is equation 1. So from 1 and 2 over here I can write this formula. Therefore I can say delta D is going to be PD square upon 4TE into 2 minus mu. So this is the formula for change in diameter for thin cylinder. We have to recollect that we are talking about two vessels over here. One is thin cylinder, one is spherical shells. So we have to talk every time about thin cylinder. So this is about the thin cylinder that we are talking. Now let's talk about the longitudinal strain. This will be EL. Now it is understood that this EL will be delta L upon L, that is change in the length upon original length, because your longitudinal strain, if you recollect, was along your, this is the entire cylinder, this is the pressure applied. So when you apply pressure like this, your length gets affected. So it is change in length upon original length. Now here, since we are talking about longitudinal strain, the important value will be longitudinal stress. So it is sigma L upon E, and the other circumferential value becomes lateral. So when I substitute, here I will write delta L by L is equal to PD upon 4TE minus mu PD upon 2T into E. Let's take out PD upon 4TE as a common term. So this becomes 1 minus 2 mu. This is delta L by L. So directly if I have to calculate delta L, I'll use the formula PdL upon 4TE 1 minus 2 mu. So this is the formula for change in length for a thin cylinder. Now last, let's talk about change in volume. This is delta V. First of all, we should know the formula for volume for a thin cylinder. It will be pi by 4 d square into L. So let's say I am differentiating this equation partially. When I say partially, obviously my volume is changing with respect to diameter and also because of length. So left hand side will become delta V is equal to pi by 4 is a constant. When I talk about partial differentiation, say I have x and y. When I differentiate with respect to x, y becomes constant. And when I differentiate y, x becomes constant. That is the logic for partial differentiation. So here, let's say I am first differentiating with respect to diameter. So length is constant. So let L be as it is. Diameter will become 2d, that is differentiation of d square, and I have to multiply with delta d because it is partial differentiation. Plus, pi by 4. For the second one, let d square be as it is, and I'll differentiate with respect to L. So this becomes delta L, because differentiation of L is 1, and I have to multiply with delta L. Now let me divide both sides with the volume. So therefore, delta V by V will be pi by 4 L into 2D into delta D upon, now rather than writing V here, I'll write this formula, pi by 4 D square L plus pi by 4 D square into delta L upon pi by 4 D square L. So you can see pi by 4 gets cancelled here, L also gets cancelled, one diameter gets cancelled. So the first term reduces to 2 delta D upon D. When I talk about the second one, pi by 4 gets cancelled, D square also gets cancelled. So what remains is delta L by L. Now we know the formula of delta D by D over here. Delta D by D is PD upon 4TE, 2 minus mu. And when I say delta L by L, it is PD upon 4TE, 1 minus 2 mu. So let's substitute. Therefore, delta V by V is equal to 2 times PD upon 4TE 2 minus mu plus PD upon 4TE 1 minus 2 mu. Now PD upon 4TE is common here for both the terms. So I have PD upon 4TE common, and what remains from here is 2 into 2 4 minus 2 into mu 2 mu, and from here I have 1 minus 2 mu. So this 4 plus 1 is 5, and these two will add up to minus 4 mu. So this is the formula for delta V by V, or I can say it is the volumetric strain if you want to write it that way. Or if you are just told to calculate the change in volume, the formula will be PdV upon 4TE 5 minus 4 mu. So this is the formula for change in volume for the thin cylinder. So with this I end the session. I hope you have understood the calculation of all the formulas. In the next session we will see numericals on this topic of thin cylinder. See you in the next session. Thank you.